Welcome to the Beyond Tech podcast, a podcast designed for engineers. We aim to demystify technologies around safety and give you the information that you need in order to make an informed decision when designing a safety system.
We cut through the fluff and we try and avoid the statements of robust and reliable, and we look at the technologies in the real world and look away from the data sheets that typically reference best case scenarios.
Each episode, we take on one gas or flame technology and break it down, how it works, when and where to use it, the potential drawbacks, and also the maintenance requirements.
In this episode, we take a look at the electrochemical sensor, the Swiss Army knife of gas detection covering many gases. And we welcome back Marcus Oertel, Product Manager. Welcome back, Marcus.
Thank you, Graham. Thanks, Megan.
Just in case you forgot, Marcus has been with Dräger for over 25 years, and 13 of them have been spent as a product manager. So, Marcus, tell us, having been with the company for so long, what is one of the highlights of your time? Maybe a favourite memory?
Oh, that's a hard question because there was several times in different roles. So, starting in the service, this was challenging, going out as a young engineer, first time to customer, and being exposed to trouble or problems they had, and figuring out how could I solve this in the field. So I would say this was the beginning, and then I figured out how interesting it is, not only just to design something, just to figure out, okay, what could be possible root causes causing the problems at the customer side.
So you like working under pressure?
I would say it could be also times there for relaxing, but under pressure, sometimes you get the best results. Look at the diamonds.
I was going to say pressure makes diamonds. So with that, let's move on to the main section. So Marcus, please tell us, how do electrochemical sensors work?
Yeah, so to make it very simple, you can compare electrochemical sensor with a battery cell. So you have a compartment where you have electrodes, you have a liquid inside, you have some kind of separators, and the electrochemical cell works in the way we want to detect certain gases, and the gases needs to create a kind of chemical reaction. So, and we want to keep, I would say, everything in the compartment. So we need a kind of membrane so that gases can vaporize in, but we want to keep our electrolyte or the liquids in, so it's not leaking.
Yeah.
So you know this.
So it's a sealed unit.
Yeah, it's like what you know from your soft shell or for sport, your jackets. So it will keep you dry from the outside, but from sweating, so the vapor, it will go out. Yeah?
Okay.
So, and similar, you have a membrane at the electrochemical sensor, so our gases we want to detect will evaporate through it. Then we have an electrode where the gas molecules will react on the surface in combination with the electrolyte. And part of this, we generate then electrons. If you have a circuitry built around the sensor, the electrons can move, and if you have a counter electrode, they can move to the opposite side, and inside you generate hydrogen ions. They move then to the counter electrode, recombine with the electrons, and then you have a circle. So it's very simple. Gas coming in, it will be, I would say, changed in a different product. Like you have CO, so carbon monoxide coming in, it will be oxidized. So product will be CO2. Yeah. And the ions that you create, they keep the circuit continuing so that the sensor can continuously measure. And the CO2 will evaporate to the outside again.
And this is all happening in like a nano or a millisecond, or nano or milli? How quick is this happening?
Yeah, so it's happening in seconds or milliseconds, we can put this. But if we speak about response time, then it's taking quite long, because when we apply the gas to the sensor, it must vaporize through the membrane. This takes time. Then it needs to be active at the electrode material and convert. So either you have a reduction or an oxidization on it. And then you need your electrons moving around. So it's time. Yeah. So we are talking about in the direction of seconds, not nano or microseconds.
Okay.
Yeah. So it's not a very fast technology.
Okay.
So if it's a chemical reaction, is it the electrolyte, is that sacrificial? Does it take away from the volume of electrolyte?
Yeah, is it used up?
That reaction?
Depends. So it depends. So they're different. So what I described is a general description. And now you have to design, I would say, your target sensor for the sensor for your target gas. So you can have an acid as electrolyte, depending what kind of gases you want to use or detect. But you could have also a base, or you could have an organic based electrolyte, or you could have a salt base. So there are a lot of different combination of electrolyte, but they're always mixed with water. Yeah. Right. So to make it more flexible inside. And the water content, this is like water can be a vapor, and we spoke about the membrane. So the water as a vapor can vaporize to the outside of the sensor. So this makes the sensor breathing. So it will be in balance with the outside. Yeah. Okay. And if you have a salt-based electrolyte, this will be used up over the time, so the content will be reduced. So there, for example, you have a limited lifetime. An acid will not be used up. Yeah. So this is a sensor which is acid-based, can easily work 10, 15 years.
Right. Which would be an acid-based? What gases can you detect with those?
Typical, you have for carbon monoxide, hydrogen sulfide, hydrogen. So these are typical acid-based. And if you go for organic vapors, this is more an organic-based electrolyte. So it really depends on what kind of gases you want to measure.
If a customer was interested in getting like an electrochemical sensor, would they need to know the gases that they were looking for when inquiring?
Sure. This is very important because I mentioned that a part of when we measure the gases, our product is always an electron. And the electron is not gas specific. Yeah? It's just an electron. And this is the amount of electron is a direct or proportional indication of the gas molecules being present. So you don't know if the electron was based by reaction with carbon monoxide or with hydrogen. So that's why we need to know what target gases or mixtures they have to see is the sensor from the design the right one, and what kind of readings he will get. Yeah, that's something we call then, you have a target gas, but yet at the same time you have cross sensitivity. So similar gases will also cause a reaction and then create electrons. So this must always be taken in consideration when you design a system with electrochemical sensor. What are the possible gases being present, so that you understand what the readings mean? Because you can have positive readings, but you could have also negative readings, because chemistry is not one way, it goes in both directions. So depending on what kind of gas you use, it can have a negative reaction and you see a negative current. So the electrons move the other way around. And on the display you see minus, for example, 5 volume% oxygen. How is this possible? By using hydrogen, applying it to an oxygen sensor, and this will jeopardize the complete process and create a negative current which is higher than the positive current of the oxygen.
Right. Wow. So we spoke a little bit about catalytic bead becoming more prevalent in the clean energy sector with hydrogen and ammonia. Can this also be said for electrochemical sensors as well?
Yeah, correct. So we have special sensors just for ammonia, different styles, depending on the ranges from ppm up to volume%, because there are different tasks to protect. So either it's toxic or it's flammable. And the same is with hydrogen, where we have two also different sensors on ppm level, but also on the low explosion limit, just to support this task. Because the electrochemical sensors have also their benefits compared to catalytic bead, especially when we look for explosion protection.
Okay.
We can detect most of the gases and vapors with electrochemical sensors. Only thing what we can't detect is gases like methane, propane, because this binding can't be broken by the chemistry. But hydrogen or ammonia are simple gases we can detect, and ammonia especially is a toxic gas, so we need to pick it up in small concentration where they are toxic, and you will smell it. Yeah, so small concentration of a few or less than 1 ppm you can smell. Yeah, it's opening your nose. And if it goes higher,
it's not a pleasant smell.
No. And if it goes higher up, you will not smell it anymore. So these gas or ammonia, for example, we can easily detect with electrochemical sensors. But as well, we can also detect hydrogen. Hydrogen is very reactive, and we use in the sensors noble materials for the electrodes, for example, platinum. And platinum can easily convert or react with the hydrogen. So it's simple to detect hydrogen with electrochemical sensors in ppm level, but also in volume percent. So we have also sensors where you can measure in the low explosion limit with electrochemical sensors. So it's no need to use a catalytic bead.
Yeah, okay.
So we looked at the cross interference of other gases. Is there anything else in the environment that could cause a shift in the reading, both positively and negatively?
Yes. When you have your mobile phone, in wintertime, you see how the battery capacity drops down if it's getting very cold. And when it's summertime, you don't see this effect. So chemistry depends on the temperature. So temperature is a huge effect how easily chemistry can operate. The other is humidity. So we need always our electrolyte to be as a liquid. So and if the height or the water content is too low, the reaction gets slowed down. And
the water content of the environment. So the relative humidity.
So sensors are always designed what we call for atmospheric conditions. So the conditions what we normally expect here in outside. So it's between I would say a few percent relative humidity up to 95, 99. So condensing you could have, but the sensors, they are always balanced with the outside, because when you, for example, have an acid, the acid will absorb the water from the atmosphere. So, and that's why we, for example, have designed the sensor in a way that it has enough volume so that it can breathe with the atmosphere. So the sensors are half full when they are manufactured, because normal and humidity is about 40%. And when you go in to Asia, for example, you have high humidity, immediately the content will increase. So if the sensor volume is not big enough, the sensor will break and will spill out the electrolyte.
So even in countries with high temperatures and high humidities, they can still use these sorts of sensors?
Yes.
Okay.
So humidity is something we can cover by the volume and the design. And temperature is something you need to consider. I mentioned the chemistry is slowing or speeding up, but you need to consider, because the effect is not linear. You have a kind of E function. So you need to measure what is the real temperature inside the chemistry to make a compensation of the signal. That comes from the effect, what we call the noise we have on semiconductors. So electrons are capable to move on a semiconductor, and if it's warmed up, they get more energy, so they can more easily jump from one point to the next. And this is then recognized as noise. So, and that means higher temperature creates higher noise, so zero reading. What we see is on sensors, when they're heated up based on a semiconductor principle, you see a zero value, or not zero anymore, fluctuating. And this effect gets higher and higher, the temperature goes up. That's why electrochemical sensors are mostly limited up to 60 degrees. Otherwise, you have a higher effect of the temperature compared to the real chemistry.
And you mentioned that the sensor was filled half full with the electrolyte liquid. Is that standard for all electrochemical sensors, or are they all the same size and shape and property-wise?
So from our side, we have 3 different sizes of sensors on the for the electrochemical style or shape, depending if they are for fixed installation or for portable. For fixed, we need to consider that they get very cold temperature, high temperature, low humidity high. If it's worn at a person, you will never be exposed to this extreme situation. So the sensor must withstand this. If we go for a base or for an acid, then they are never fully filled, so that we have enough space. If we are talking about sensors which use a different kind of electrolyte which will evaporize, then it's close to almost filled. So it really depends what kind of electrolyte is used, because then the volume defines the lifetime of the sensor, because it will evaporize over the time. And if it's empty, it's like the battery, like the alkaline, then you can't use it anymore.
So how should engineers look at cross-sensitivity? Is there other ways of filtering out that potential cross-sensitivity?
So what we do is normally we provide a lot of documentation, specification sheets, where we show up what are typical gases and vapors which could have an influence to the sensor, and how high is the influence to it. So to get an understanding, if I use, for example, a carbon monoxide sensor in industry and then I have hydrogen present, this could cause a reading. Right. And in the end, you don't know, is it caused by the carbon monoxide or the hydrogen? There are special versions which have a low cross-sensitivity towards hydrogen, but you need to know, okay, is hydrogen present in my application, and could this give a reading to the sensor? So it's important to know roughly what are the main gases, vapor present, especially depending on what is the measuring range of the sensor. So if we are talking about ppm, we should also look to other gases in the ppm range. Yeah.
Okay. And then looking at the installation and the commissioning phases, what sort of considerations do we need to take care of when?
I mean, it looks easy to install, right? I guess you just insert it.
Yeah. Yeah. What we have here are smart sensors. So they are calibrated in the factory. So they have on the back side a PCB with a memory on site where all the relevant data are stored. From the production and for the operation. So when you plug it in one of our transmitters, the transmitter will read out what kind of sensor it is for target gas, measuring range, all the relevant settings for alarm, and also information about calibration. So, and when the sensor is starting to measure, it needs to know what is the relative sensitivity of the sensor to give the proper reading. And every time when you calibrate the sensor, these information are stored back in the memory, so you can unplug the sensor and use it somewhere else without recalibration.
Okay.
So,
and when you first install these sensors, do they have a long warm-up time, or are you able to start detecting straight away?
It depends. So because there are two possibilities. We have smart transmitters which have an accelerated warm-up time. So we use a higher current so what you need inside is you need a balanced chemistry. So the electrode needs a certain bias level. And for this is what we call the warm-up time. So otherwise the sensor will not detect the gases. So if the sensor is a zero bias, so there's no difference because we're using third electrodes. If there's no difference on the bias, then it goes quite fast. If you have, I would say, more specific sensors for certain gases, we need to arrange the sensor or apply a certain bias, and then it takes longer. With the principle of these accelerated warm-up, we apply the current, measure what is the potential between the electrodes, and adjust. So it's a loop-based.
Okay.
If you have not smart transmitters, there are also transmitters which are very simple. They just have a timer running down, so they are not actively measuring what is the bias or the voltage between the different electrodes to compensate.
Okay.
So that can go then easily from 1 hour up to 24 hours.
So something to bear in mind if you're trying to get up and running straight away.
Yeah.
Yes.
So, but there's also sensors which can run in a few minutes. Yeah. So it really depends what kind of chemistry is inside.
Okay. And can you tell us a little bit about standards that are applicable that maybe some people may have some misconceptions on?
Sure. So from, I would say, explosive or explosion protection, we know there are a lot of standards regulating what kind of sensors you're allowed to use, about the performance. And we have something similar on the toxic level. So now, in the past, we had a lot of national requirements. Companies like oil and gas companies had their own internal standards because there was nothing on the, I would say, on the European or international standard. Now with the IEC, we have a standard which is called the EN, so it's also for Europe valid, IEC 62990-1. This is a performance standard for toxic gases, and we look on toxic gases on two sides. One is means for working, so safety. Okay. So we need to observe, is the concentration hazardous for the worker? And the second is what we call the level, looking for possible leakages. So health monitoring, safety monitoring. So this is what you could do with toxic gas detectors. So protecting people or protecting assets. So this is both described in the standard, and the sensors, it's not limited, I would say, to electrochemical sensor. You could use also other technologies, but it's described how the sensors needs to be tested to fulfill certain requirements on the accuracy. Because when we talk about health monitoring, so the safety of the people, then it's very important that we accurate measure, because we are talking about 1 or 5 ppm as a workplace threshold for certain gases, which is very low.
It's fine margins.
Yes, and but on the safety level, if we are looking for, I would say, possible leaks, then it's the requirement is not as high. Both requirements or topics are described in the standard. You can approve your products, and the benefit of these kind of standards is IEC is international. So if you go for one notified body, for example in UK or the Netherlands, you can use the certificate all over the world where IEC is accepted. And interesting is the IEC, or also countries like US or Russia or China, they use their national systems are based on the IEC. So you're very close to that. Maybe there are some national deviation, but if you have an IEC certificate, you can utilize it for entering other countries or regions.
Yeah, oh, that's interesting.
So important when you're specifying a product from maybe one country, and you're going to install it in another country, then the 62990-1 is kind of your universal, your safe bet. So if your device complies to that, it's a
good
safer
device.
option. When going cross border.
And the good thing is they used a similar approach like for flammable gases. So when you use the flammable and go through the standard, you will see there are a lot of common things. And this is for manufacturers, so for companies like us developing manufacturing products. And for the user, there's a -2. So this is a guidance how to select the right sensor technology, how to install it in the right way, how to maintain it. And this is the same on flammable. So you have a guidance which is always related to the performance and also on the usage.
I'm going to go out on a whim and say that this is light nighttime reading.
Yeah.
We understand it, so you don't have to. So, like any sensor, there needs to be some maintenance after the installation. Can you describe the kind of considerations you take into account when using electrochemical?
It's maybe a little bit different for flammable. Flammable is quite easy, as we are always talk about higher concentration. On toxic gas, normally we have a low concentration on ppm level. That means how you apply the gas, how you do the calibration requires more, I would say, routines and accuracy to get a proper calibration or adjustment in the end. So we always recommend to use the target gas, so that the sensor is calibrated with the gas you want to detect, but also mostly to be calibrated under the condition how you want to use it. So humidity or temperature can be compensated. So, but for example, if you measure in a duct because you have a ventilation system in which needs to observe for possible hydrogen sulfide, you need to switch off, then you need to consider this airstream because this will have an impact on your readings. So it's not the chemistry, but it's the amount of gas which will be provided to the sensor for the reaction.
And does the sensor always need to be where the gas is, or can it be like a remote, or like through the use of a pump, for example?
Sure. So the gas needs to come to the sensor, So that's the point. And the best is always by diffusion, because this is how the principle is designed. When you have an application where it's difficult to define where is the possible leakage, or you have an application like in pharmacy where you need to use hydrogen peroxide to clean the room and you need to control it, then it's difficult where to position. So normally then you either use remote sensors at different places, or you use a sampling system to suck air probes from the application and apply it to the gas. Important is always when you design systems or you use sensors, as gases, especially in the toxic area, can react with surfaces, like hydrogen peroxide. The idea is to clean surfaces so as they stick to surfaces. So you need to understand what are the property of your gas, so that you understand why, for example, it takes time before the gas will reach the sensor, and also how long it takes to decline. Or opposite way, you want to use chlorine. Chlorine will also react with a lot of surfaces, and if you use a long hose in between, the surface needs first to be saturated before the gas reaches your sensor. For calibration, very important. You see, signal goes up, looks stable. Okay, confirm. No, it was too short. So you need to understand a little bit the impact of surfaces to your gases before you can really be sure that you measure the right concentration.
And I'm sure that's something that's pretty overlooked as well within industry.
Yeah.
So going back to the calibration, and we talked about humidity, calibration gas in its cylinder tends to be dry, right?
Yeah.
Does that need to be, how does that work with and then exposing it to the same concentration but with a sort of humid atmosphere?
So yes, normally it would be better to have calibration gas which is not completely dry, and also normally you get it balanced with nitrogen. This is also which we didn't talk about. The process of the sensors is always driven by using oxygen. So we need always oxygen in the process. There are only a few gases where you don't need oxygen present. The first is an oxygen sensor, so you want to measure the concentration dropping down. If there's no oxygen, no problem. Yeah. The others are acid compounds. There it's in principle different. There we don't speak about oxidation. There it's a different setup. But for calibration, coming back to this point, the sensor itself, in the electrolyte, you have humidity, you have oxygen. So for the period of 5 minutes, 30 minutes, it's no problem to compensate the effect of the dry calibration gas.
Okay.
Different is if you would use it in a process to observe all the time. For example, you have a pipe where you want to measure CO because it's needed in a process and it's completely dry. Then it's a question of time when the sensor will be dried out, so level is too low, or the oxygen is used up. For this kind of things, you need to have a time that the sensor can recover. So you need a kind of bypass so that you can flood the sensor with fresh air. So in between, so that it can. It's like diving. Yeah, you can stop breathing for this moment, but at a certain point of time, you need to come up again.
Okay.
Yeah.
Without a bottle of gas on your back, but
Yeah, but even with that, So how long you can stay down?
Yeah, absolutely.
I'm too scared of sharks. No.
So we like to take some takeaways. So we'd like to summarize 3 points that our viewer can take away from this video. So the 3 questions, I'll start with the first one. When would electrochemical sensors be the correct choice?
Every time when we look for substances either which are toxic directly or also in long term, in low concentrations, so talking about ppb, ppm, maximum up to volume %. Yeah, this would be the best choice, and if we have the right environmental conditions for the sensor, so talking about humidity and also oxygen.
Okay.
And the biggest limitation or misconception that people often have?
This is about not understanding, for example, that we have an oxidation or reduction process inside, keeping in mind we need oxygen inside, but also the problem of having just what we talk about dry air, so that the lifetime suddenly they're surprised that the sensor is not lasting very long because the liquid is vaporized.
Yeah.
And the last one is what's the one thing to remember regarding maintenance?
The one thing is always to keep in mind when you have gases which are, I would say, are reactive or corrosive, to keep in mind to keep or select the right calibration equipment. So short hose, the right pressure reducers, the right adapter, because material will always react with it. And this is, I would say, one of the common mouse traps that people, for example, disassemble the pressure reducer on chlorine or HCl and wonder why it's not working afterwards. Because you have corrosion on the surfaces and suddenly you have different concentration coming out of the cylinder.
Okay.
Very good. So that's a wrap. Thank you very much, Marcus. That was very insightful.
Thank you.
Welcome.
So that's another episode of Beyond Tech podcast. If you have any projects that you need a deeper understanding of the technologies, then please go to Dräger.com/EPC, where you have a whole library of information you can download there.
We hope you found the podcast useful and informative. And as always, if there's anything you'd like to know further, please let us know.
So on to the next episode, where another technology we will discuss. But the rules are the same. So no fluff, no product, and what survives a real project.
Thank you.
Thank you.